Quantum entanglement is a physical phenomenon that occurs when pairs or groups of particles are generated or interact in ways such that the quantum state of each particle cannot be described independently. Instead, a quantum state may be given for the system as a whole. Measurements of physical properties such as position, momentum, spin, polarization, etc., performed on entangled particles are found to be appropriately correlated. For example, if a pair of particles is generated in such a way that their total spin is known to be zero, and one particle is found to have clockwise spin on a certain axis, then the spin of the other particle, measured on the same axis, will be found to be counterclockwise because of the nature of quantum measurement. However, this behavior gives rise to paradoxical effects. Any measurement of a property of a particle can be seen as acting on that particle, and in the case of entangled particles, such action must be on the entangled system as a whole. It thus appears that one particle of an entangled pair knows what measurement has been performed on the other, and with what outcome, even though there is no known means for such information to be communicated between the particles, which at the time of measurement may be separated by arbitrarily large distances. Such phenomena were the subject of a 1935 paper by Albert Einstein, Boris Podolsky, and Nathan Rosen, and several papers by Erwin Schrödinger shortly thereafter, describing what came to be known as the EPR paradox. Einstein and others considered such behavior to be impossible, as it violated the local realist view of causality and argued that the accepted formulation of quantum mechanics must therefore be incomplete. Later, however, the counterintuitive predictions of quantum mechanics were verified experimentally. Experiments have been performed involving measuring the polarization or spin of entangled particles in different directions, which, by producing violations of Bell's inequality, demonstrate statistically that the local realist view cannot be correct. This has been shown to occur even when the measurements are performed more quickly than light could travel between the sites of measurement. There is no light speed or slower influence that can pass between the entangled particles. Recent experiments have measured entangled particles within less than 1/100% of the travel time of light between them. According to the formalism of quantum theory, the effective measurement happens instantly. It is not possible, however, to use this effect to transmit classical information at faster than light speeds. Quantum entanglement is an area of extremely active research by the physics community, and its effects have been demonstrated experimentally with photons, electrons, molecules the size of buckyballs, and even small diamonds. Research is also focused on the utilization of entanglement effects in communication and computation. History. The counterintuitive predictions of quantum mechanics about strongly correlated systems were first discussed by Albert Einstein in 1935, in a joint paper with Boris Podolsky and Nathan Rosen. In this study, they formulated the EPR paradox, a thought experiment that attempted to show that quantum mechanical theory was incomplete. They wrote, "We are thus forced to conclude that the quantum mechanical description of physical reality given by wave functions is not complete." However, they did not coin the word entanglement, nor did they generalize the special properties of the state they considered. Following the EPR paper, Erwin Schrödinger wrote a letter to Einstein in which he used the word Verschränkung to describe the correlations between two particles that interact and then separate. As in the EPR experiment, he shortly thereafter published a seminal paper defining and discussing the notion, and terming it entanglement. In the paper he recognized the importance of the concept, and stated, "I would not call entanglement one but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought." Like Einstein, Schrödinger was dissatisfied with the concept of entanglement, because it seemed to violate the speed limit on the transmission of information implicit in the theory of relativity. Einstein later famously derided entanglement as Spuk-after-Fernwirkung, or spooky action at a distance. The EPR paper generated significant interest among physicists and inspired much discussion about the foundations of quantum mechanics, but produced relatively little other published work. So, despite the interest, the weak point in EPR's argument was not discovered until 1964, when John Stuart Bell proved that one of their key assumptions, the principle of locality, which underlies the kind of hidden variables interpretation hoped for by EPR, was mathematically inconsistent with the predictions of quantum theory. Specifically, he demonstrated an upper limit, seen in Bell's inequality, regarding the strength of correlations that can be produced in any theory obeying local realism, and he showed that quantum theory predicts violations of this limit for certain entangled systems. His inequality is experimentally testable, and there have been numerous relevant experiments, starting with the pioneering work of Friedman and Clauser in 1972 and Aspects experiments in 1982. They have all shown agreement with quantum mechanics rather than the principle of local realism. However, the issue is not finally settled, as each of these experimental tests has left open at least one loophole by which it is possible to question the validity of the results. The work of Bell raised the possibility of using these super-strong correlations as a resource for communication. It led to the discovery of quantum key distribution protocols, most famously BB84 by Bennett and Brassard and E91 by Arthur Eckert. Although BB84 does not use entanglement, Eckert's protocol uses the violation of a Bell's inequality as a proof of security. Concept. Meaning of entanglement. An entangled system is defined to be one whose quantum state cannot be factored as a product of states of its local constituents. If entangled, one constituent cannot be fully described without considering the other. Note that the state of a composite system is always expressible as a sum, or superposition, of products of states of local constituents. It is entangled if this sum necessarily has more than one term. Quantum systems can become entangled through various types of interactions. For some ways in which entanglement may be achieved for experimental purposes, see the section below on methods. Entanglement is broken when the entangled particles decohere through interaction with the environment, for example, when a measurement is made. As an example of entanglement, a subatomic particle decays into an entangled pair of other particles. The decay events obey the various conservation laws, and as a result, the measurement outcomes of one daughter particle must be highly correlated with the measurement outcomes of the other daughter particle. For instance, a spin-0 particle can decay into a pair of spin-1/2 particles. Since the total spin before and after this decay must be zero, whenever the first particle is measured to be spin up on some axis, the other is always found to be spin down. Paradox. The paradox here is that a measurement made on either of the particles apparently collapses the state of the entire entangled system, and does so instantaneously, before any information about the measurement could have reached the other particle. In the quantum formalism, the result of a spin measurement on one of the particles is a collapse into a state in which each particle has a definite spin along the axis of measurement. The outcome is taken to be random, with each possibility having a probability of 50%. However, if both spins are measured along the same axis, they are found to be anti-correlated. This means that the random outcome of the measurement made on one particle seems to have been transmitted to the other, so that it can make the right choice when it is measured. The distance and timing of the measurements can be chosen so as to make the interval between the two measurements space-like, i.e., from any of the two measuring events to the other a message would have to travel faster than light. Then, according to the principles of special relativity, it is not in fact possible for any information to travel between two such measuring events. It is not even possible to say which of the measurements came first. as this would depend on the inertial system of the observer. Therefore, the correlation between the two measurements cannot appropriately be explained as one measurement determining the other. Different observers would disagree about the role of cause and effect. Hidden variables theory. A possible resolution to the paradox might be to assume that the state of the particles contains some hidden variables, whose values effectively determine, right from the moment of separation, what the outcomes of the spin measurements are going to be. This would mean that each particle carries all the required information with it, and nothing needs to be transmitted from one particle to the other at the time of measurement. It was originally believed by Einstein and others that this was the only way out, and therefore that the accepted quantum mechanical description must be incomplete. Violations of Bell's inequality. The hidden variables theory fails, however, when we consider measurements of the spin of entangled particles along different axes. If a large number of pairs of such measurements are made, then statistically, if the local realist or hidden variables view were correct, the results would always satisfy Bell's inequality. A number of experiments have shown in practice that Bell's inequality is not satisfied. However, all experiments have loophole problems. When measurements of the entangled particles are made in moving relativistic reference frames, in which each measurement occurs before the other, the measurement results remain correlated. The fundamental issue about measuring spin along different axes is that these measurements cannot have definite values at the same time. They are incompatible in the sense that these measurements' maximum simultaneous precision is constrained by the uncertainty principle. This is contrary to what is found in classical physics, where any number of properties can be measured simultaneously with arbitrary accuracy. It has been proven mathematically that compatible measurements cannot show Bell inequality violating correlations, and thus entanglement is a fundamentally non-classical phenomenon. Other types of experiments. In a 2012 experiment, delayed choice entanglement swapping was used to decide whether two particles were entangled or not after they had already been measured. In a 2013 experiment, entanglement swapping has been used to create entanglement between photons that never coexisted in time, thus demonstrating that the non-locality of quantum mechanics, as manifested by entanglement, does not apply only to particles with space-like separation, but also to particles with time-like, i.e., temporal, separation. In 3 independent experiments it was shown that classically communicated separable quantum states can be used to carry entangled states. In August 2014, researcher Gabriela Barreto Lemos and team were able to take pictures of objects using photons that have not interacted with the subjects, but were entangled with photons that did interact with such objects. Lemos, from the University of Vienna, is confident that this new quantum imaging technique could find application where low-light imaging is imperative, in fields like biological or medical imaging. Special theory of relativity. Another theory explains quantum entanglement using special relativity. According to this theory, faster-than-light communication between entangled systems can be achieved because the time dilation of special relativity causes time to stand still, in light's point of view. For example, in the case of two entangled photons, a measurement made on one photon at present time would determine the state of the photon for both the present and past at the same moment. This leads to the instantaneous determination of the state of the other photon. Corresponding logic is applied to explain entangled systems, i.e., electron and positron, that travel below the speed of light. Mystery of time. There exist physicists who say that time is an emergent phenomenon that is a side effect of quantum entanglement. The Wheeler-DeWitt equation that combines general relativity and quantum mechanics, by leaving out time altogether, was introduced in the 1960s and it was taken up again in 1983, when the theorists Don Page and William Wurters made a solution based on the quantum phenomenon of entanglement. Page and Waters argued that entanglement can be used to measure time. In 2013, at the Istituto Nazionale di Ricerca Metrologica in Turin, Italy, Caterina Mareva, together with Giorgio Brida, Marco Gramegna, Vittorio Giovannetti, Lorenzo Macconi, and Marco Genovese performed the first experimental test of Page and Waters' ideas. Their result has been interpreted to confirm that time is an emergent phenomenon for internal observers but absent for external observers of the universe. According to Lloyd, the arrow of time is an arrow of increasing correlations, non-locality and hidden variables. There is much confusion about the meaning of entanglement, non-locality and hidden variables and how they relate to each other. As described above, entanglement is an experimentally verified and accepted property of nature, which has critical implications for the interpretations of quantum mechanics. The question becomes, how can one account for something that was at one point indefinite with regard to its spin suddenly becoming definite in that regard even though no physical interaction with the second object occurred, and, if the two objects are sufficiently far separated, could not even have had the time needed for such an interaction to proceed from the first to the second object? The latter question involves the issue of locality, i.e., whether for a change to occur in something the agent of change has to be in physical contact with the thing that changes. Study of entanglement brings into sharp focus the dilemma between locality and the completeness or lack of completeness of quantum mechanics. Bell's theorem and related results rule out a local realistic explanation for quantum mechanics. However, in other interpretations, the experiments that demonstrate the apparent non-locality can also be described in local terms. If each distant observer regards the other as a quantum system, communication between the two must then be treated as a measurement process. And this communication is strictly local. In particular, in the many worlds interpretation, the underlying description is fully local. More generally, the question of locality in quantum physics is extraordinarily subtle and sometimes hinges on precisely how it is defined. In the media and popular science, quantum non-locality is often portrayed as being equivalent to entanglement. While it is true that a bipartite quantum state must be entangled in order for it to produce non-local correlations, there exist entangled states that do not produce such correlations. A well-known example of this is the Werner state that is entangled for certain values of but can always be described using local hidden variables. In short, entanglement of a two-party state is necessary but not sufficient for that state to be non-local. Moreover, it was shown that, for arbitrary number of party, there exist states that are genuinely entangled but admit a fully local strategy. It is important to recognize that entanglement is more commonly viewed as an algebraic concept, noted for being a precedent to non-locality as well as to quantum teleportation and to superdense coding, whereas non-locality is defined according to experimental statistics and is much more involved with the foundations and interpretations of quantum mechanics.